So the major objective is understanding what's the vector equation of line and how do we write down equation of line in three dimension. Cartesian form, vector form, and parametric form. These three are the forms that we need to study for the AAHL course. And how can we interchange these forms from one to the other? And what's so special about these forms is uh, something like, how when do we use each of the different forms. So in the first like 10 minutes, we'll first understand the vector equation of line and what exactly is the need for writing equation of line in vector form. So you might have already come across the first thing, which is y equals to mx plus c. Um, this is referred as the Cartesian equation of line in two-dimensional form. So when you have a line basically in xy plane, and you write down here with the certain slope and certain y-intercept. So that's your slope, and this is the y-intercept. We call this as y equals to mx plus c form. The problem with this form is that this form doesn't account the height factor. Okay, so when you look at the height factor, now, for example, let's say in three dimensional, so let's say there is a bird sitting on the top of one building, okay, and then it jumps and let's say it flies to the other top of the other building. So let's say here is the other building. Now, let's say this flew in a straight line path to sit here. The problem is that like this form cannot express the height. So it might express the x and y coordinate, but the height factor is something that is missing. So we need something better. We need something that can help us to get the height. Now, as you know that in two dimension, your height is not in picture. In three dimension, whenever we write a vector, ABC. So if I show you here the x, y, and z coordinates, so let's say x, y, and z. So if I actually show this vector here from origin, this is the origin. I'm moving a units to the right, so you can see a to the right, which is this. Then b units along y, and c units along z axis. So this actually the factor, the z coordinate actually is the height factor. So this, if we express a motion of a line in vector form, which is nothing different, we have been always doing it. One of the very common relation that you might be learning is v equals to u plus at. This is like a vector equation itself. Like v is the velocity, final velocity, which is initial velocity, and acceleration, and t is the time. So I'm going to just make use of something like on similar line to write down the vector equation of line. So how do we begin up with this? So let's say if I have an initial point x, x1, y1, and z1. And so let's say there is certain direction in which this vector is going. And that direction is referred as, let's say, I take it as direction vector b. I can express that like in component form, like let's say it's a1, b1, and c1. Now, how do I write down the equation of this line? So whenever you have been given direction of a line, the vector equation of line is actually given by r equals to a plus lambda b. Now I'll decode this form. What does each of them stand for? So a is basically the initial position or initial coordinate or any coordinate on the line where motion is starting from. B is referred as direction vector. Lambda is referred as something called as parameter. And r is nothing but general xyz coordinate at any given parameter value. Now, for example, let's say that there is a bird which is sitting here at 1, 2, and 3. Coordinate is position vector is 1, 2, and 3. And its direction vector is, let's say, 1, 1, and 3. So here what is happening is the vector equation of this line will be 1, 2, 3. plus, let's say t. Instead of this lambda, I can take any parameter, any constant I want. T times 1, 1, and 3. So that's your vector equation of this line. Now, what is so special about this line? So let's say if I take x, y, z, and r is nothing but x, y, z. So if I take now time as 0, this is t is the parameter. So time, it can be time parameter, rate parameter, anything. So most of the time in real life, real world example, t is the time or lambda is the time too. So x, y, z is 1, 2, 3 plus t times 1, 1, and 3. So if I take, let's say, what's the initial coordinate? So in that case, I plug t as 0. So it'll be 1, 2, and 3 itself. So the initial coordinate is it's at 1, 2, and 3, which is very obvious. Now, if I wanted to find out where is the particle after, let's say, 2 seconds. So if I find out where is the particle after 2 seconds, if you plug in t as 2 here, so you're going to get x, y, z coordinate is equals to 1, 2, and 3 plus 2 times 1, 1, and 3. So this becomes basically, if you take simplify this, so it becomes 1 plus 2, comma 2 plus 2, comma 3 plus 6. So the final coordinate is 3, comma 4, comma 9. So according to this motion, you can see that the particle is, let's say if it started at 1, 2, and 3 somewhere here, it is now at 3, 4, and 9. So 3, 4, and 9. So this is 1, 2, and 3. So, if anybody asks what's the height of this from the initial position, you can say the height is 6. So this is where the height factor is taken care. So 3 and 9 here. So the height factor is 9 minus 3, which is 6 basically. So this is where this form comes very handy. And when you're writing the vector equation of line, it is important that you understand each term. So I just repeat again, R is the any general coordinate. A is the initial point from which the motion begins. B is the direction vector. Generally, like in motion problems, it is velocity vector. We call it as a velocity vector. You can see here, 1, 1, 2, 1, 1, 3 is like a velocity or displacement vector, you can say. So this is the basic part of the vector equation of line. So here is another example. Let's say a particle is passing through the two coordinates 1, 2, and -3, and second coordinate b is 2, 1, and 5. And you have to find out the vector equation of line joining these 2 points. Very common question. So in diagram form, if it is 1, 2, and -3, that's the position. 1, 2, and -3 is the coordinate of point A. Coordinate of point B is 2, 1, and 5. So first thing is that in order to get the vector equation of this line, you need 2 things. R equals to A plus, let's say, TB. A is nothing but the initial point. So I can take this or this, any one point you want. So let's say I pick up 1, 2, 3, -3, but still I don't have the direction vector. So you can clearly understand the direction vector is AB. If I find out vector AB, that becomes my direction vector. So AB is basically coordinate of B minus coordinate of A, or position of B minus A. So 2, 1, and 5 minus 1, 2, and -3, which is 2 minus 1 is 1. 1 minus 2 is -1. 5 minus and minus 3 is 8. So 1, -1, and 8. So that's basically the direction vector. Very interesting thing is that you could take the direction vector also as -1, 1, and -8. So you can take a scalar multiple of the direction vector, because your sense of travel might change. Your sense of travel might be now this way, but you're still representing that line. So this is about the direction vector. Now, the final equation is going to be R is 1, 2, and -3 plus T times the direction vector I can take is 1, -1, and 8 here. Other way you could write the equation was that I could take this B also as my initial point. I could take, so my new equation can be, so this, or it can be 2, 1, and 5. That's my initial point. Plus, let's say, take a different parameter. Take a different parameter now, as because you, even though somebody starting its motion from here and going along this line, or somebody starting from here and going along this line, it's okay. It can go in this sense or it can go in this sense, doesn't matter, as long as I'm getting the same line. So it can be written as s times 1, -1, and 8, or you could take the scalar multiple of this direction. I could take 2, -2, and 16 also. I could take this direction vector. Anything is fine as long as you're writing the correct equation of the same path. So for this particular problem, we have a crow flying from -1, -3, 7 to 2, 8, and 4 in 5 seconds. You have to write down equation for this path in vector form. So first thing is that you need initial point. Initial point is basically -1, -3, and 7. And you need direction vector or velocity vector. So first you find out displacement. So displacement vector, because here they have given time. So time is a very important thing out here. So in every second, how much is the displacement? So first you find displacement in 5 seconds. So final coordinate is 284. Minus initial is -1, -3, and 7. So that is nothing but 3. 8 minus and -3 is 11. And 4 minus 7 is -3. So that's your displacement vector in 5 seconds. So find out displacement in 1 second, because you'll be putting the time parameter. So you need to use the velocity vector. So velocity vector is basically 3 over 5, 11 over 5, and -3 over 5. Because this displacement happened in 5 seconds. You can't just take this as the direction vector. Because whenever it is a motion problem, it is always, remember, r equals to a plus lambda b, or r equals to a plus db. B is always the velocity vector. So r equals to, what we get is, a is -1, -3, and 7, plus t times 3 over 5, 11 over 5, and -3 over 5. And you know what? If you take time t as 5, you will get the exact this coordinate. If you put t as 5 here, you can see that you're getting this exact coordinate 2, 8, and 4. If you put t as 5, you can see this 5 get cancelled. So 3 and -1 is 2, 11 minus 3 is 8, and -3 plus 7 will become 4. So this is a easy way to check in. Now, let's say if I asked to find out what's the speed of this crow while it flew from here to here. So if I wanted to find out speed, I'm just going to take the magnitude of velocity vector. So magnitude of velocity vector is called as speed. So here, if I take the speed of this, it is 3 by 5 squared plus 11 by 5 squared plus -3 by 5 the whole square. And you guys take the square root of this. So this is how you find out the velocity vector. The speed. All right, so now we're going to switch to the next part, which is different forms of line. So forms of lines is basically, we studied one of the form just now, which is referred as r equals to a plus tb, which is also referred as vector form. And now next up is we have got something called as Cartesian form. Cartesian form. So if I have got r is a plus tb, let's say r is x, y, z, and then, sorry, there is one more, is parametric form. So if I've got x, y, z as r, and a, if I take, let's say a is x1, y1, and z1, and let's say the direction vector is b1, b2, and b3. So that's my direction vector. This is the initial point. And so I can write this equation as x1, y1, and z1 plus b times t times b1, b2, and b3. So now when you write down this equation, um, by simplifying the right hand side, so you get x will be x1 plus t times b1. Y is going to be y1 plus t times b2. Z is z1 plus t times b3. This equation is referred as parametric form. Parametric form of the line. So basically, you have converted a vector form into a parametric form by just doing simple operation. Now I'll give a parallel example. So let's say a line is 1, -1, and 2 plus t times 2, 1, and 1. And I want to write down this equation in parametric form. So there's going to be 1 plus 2t. So this is 1 plus 2t, -1 plus t, and 2 plus t. So if you simplify this, that's your x, y, and z coordinate. So parametric form is any general coordinate on that given line for fixed t value. So if you put t value as 1, I'll get one coordinate. T as 2, I'll get second coordinate. That's why this is referred as a parametric form, because equation is purely depending upon t values. Second form is the Cartesian form. Actually, Cartesian form is something that we have always studied, which is in terms of only x, y, z. So now if I make from here t the subject, so you will get t the subject. If I make, it will be x minus b1 upon x minus x1 upon b1, and similarly t is y minus y1 upon b2, and similarly t will be z minus z1 upon b3. So since if you just solve for t, you will get these respective equations that I have written. Now, since my left hand side is the same for all of them, I can equate the right hand side. So my parametric form can be converted to Cartesian form by just one single step. I'll just now equate the format, equate the form that I have got here, which is this. So it'll become x minus x1 upon b1 equals to y minus y1 upon b2 equals to z minus z1 upon b3. So this is also referred as the Cartesian form of line. So it's very simple if you remember that this passes through x1, y1, z1, and the direction vector is the denominator ratios b1, b2, and b3. It makes life much more easier. So if you wish to write down this in Cartesian form, I know since this line passes through 1, -1, and 2, so the equation will become x minus 1 upon 2 equals to y plus 1 upon 1 equals to z minus 2 upon 1. So 2, 1, 1 goes to denominator, 2, 1, 1, and 1, -1, and 2 is x1, y1, and z1 value respectively. So this equation is basically the Cartesian equation of the line. Mainly you will be using the parametric form and vector form, but sometimes you're given lines in Cartesian form. That's why I have kind of explained you for your knowledge. So we've got two questions here now. The first one is that if you have got r is -1, -1 and 3 plus t times 2, -1 and 5 as one of the equation, you got to write down this in parametric and Cartesian form. So first thing is that, as we know, we got to make the r as x, y, z. So x, y, z is your r value in general coordinates. It is -1, -1 and 3 plus t times 2, -1 and 5. So this become -1 plus 2t, -1 minus t, and 3 plus 5t. That's your parametric form. For Cartesian form, since you know the direction, you could manually make the subject, like you could make t the subject from here. So it'll become x plus 1 upon 2. Similarly, you could make t the subject here. So it'll become y. T will be equals to y plus 1 upon -1. And then you can make t the subject will be z minus 3 upon 5. and equate them. So it'll become x plus 1 upon 2 equals to y plus 1 upon negative 1 equals to z minus 3 upon 5. So automatically get the same equation, or you could use the standard format, x minus x1 upon b1 equals to y minus y1 upon b2 equals to z minus z1 upon b3. So any of this is okay. Now, next question is, you have been given an equation in Cartesian form. You have to write in vector and parametric form. So what I advise here is that instead of reading this equation, because here you see that the coefficient of y is not 1, so you'll need some adjustment in order to make coefficient of y 1 and throw to denominator. So it is always recommended that you take this as parameter t, equate them as parameter t, and now make x the subject, y as a subject to get the equations in parametric form. So x will be phi t plus 1. You can see phi multiplied by t and then move 1 to the other side. And similarly, y is going to be, if I make 2y minus 3 equals to t, so y is going to be t plus 3 upon 2, and z will be 7t plus 1. So finally, our equation parametric form is, if I write down all together, r equals to x is 1 plus phi t, y is 3 by 2 plus t by 2, and z is 1 plus 7t. And if I isolate these terms one step backwards, I'll get the vector form. So 1, 3 by 2, 1 plus t times 5 half and 7. So this is how you kind of do this particular question, converting lines in different form.